Okay. Hi, everybody. Welcome back. Thanks for your patience with needing to reschedule the classes from last week. Those will be rescheduled to this Friday and the following Friday. If you can make it, good. If not, don't worry about it. The lectures will be posted on the class website. And so we'll just kind of make up the lectures that way. We went through, and we kind of went up through Chapter 7 and Chapter 8 in the book, which have to do with high cycle fatigue, right? Lots of cycles, like tens of thousands, hundreds of thousands. And we worked a lot with those SNP curves. And then we went on to talk about damage accumulation. And we talked about damage accumulation in sort of theoretical terms, like conceptual terms, right? So if you go X amount of cycles at X amount of load, you account for mean stresses, then you accumulate some amount of damage. And then if you continue to have cycles beyond that, you accumulate more damage. But that does not specify what the damage actually is, with the exception of, I think it was the last rule we looked at, which was that double linear rule for damage accumulation. And it said that we're going to still theoretically now, conceptually, break the damage up into the damage leading to crack initiation and then the damage leading to crack propagation. And so then we had these two phases, and we had to add up the damage to see if a crack would initiate, and then go into the second phase and add up the damage to see if a crack would propagate. Right? And we had sort of this hypothetical crack. We didn't know the size of the crack, where the crack was, anything about the crack, right? And so that's one way of approaching modeling of fatigue in materials. So lots of cycles, they could be fluctuating. And we'll return to that one more time when we talk about sort of random loads and how to think about that. So that's one sort of body, which is high cycle fatigue. And the name of the, I guess, overarching approach that we used was called stress life, because it was SNP, right? Stress, number of cycles, which is life, and then our reliability. And so that was a stress life approach. And it very much came out of the way that we look at static failure in materials, right? So when we're doing a static failure criterion for, let's say, yielding, we would have a metric, right? Yield stress. We'd apply some failure criterion, apply it to the yield stress, and see where we fall. So it very much came out of that. And we are going to think about we're going to start thinking about the second way of considering damage today, because we need it as a background before we go back and do something a little more sophisticated. And so the second type of, I guess, way of thinking about fracture in mechanical components is through fracture mechanics. And so this is not going to consider, let's say, only the stress in an abstract way at a local place on a part, and sort of modeling everything blind where we don't look at the crack, right? So now we're going to open up our eyes, and we're actually going to look at the size of the crack. And we're going to talk about fracture mechanics in terms of the size of that crack and what it does to the stress field right at the crack tip, and then what that means globally when we're applying a stress, like far away from that crack. And so I showed you the example of the Comet aircraft in the last lecture. And we talked about sort of the way that they designed it, right? Which was for safe life, which they said it needs to hit this life. We designed it to be safe until that life, but they didn't realize that they were stacking their proof testing in such a way where they pre-stressed the material and induced residual stresses that they way overestimated what they could sustain. And so that was one example of how the advent of new, let's say new technology like jet engines meant that they had to consider new things when designing the fuselage body. And so their need to kind of design that after the jet engine sort of outpaced the understandings of fatigue. And so that process of some advance outpacing the understanding of fatigue has happened many times throughout history. So if you want to read more about that, the first paragraph in chapter 3 in section 3.7 gives a few examples of that. So that's what we're going to be looking at today. And so they gave a few examples of how like materials development outpaced fatigue, right? Or these structural designs outpaced the ability to analyze them for fatigue. And so that's kind of both the benefit and the drawback, right, of innovation is that we get these awesome new things, but then we have to figure out how to use them, right? And so linear elastic fracture mechanics, this type of analysis started coming on around the same time after those Comet aircraft failures in the 1950s, and thinking more about that cascading kind of safe design where if one thing breaks, then you accommodate those stresses in another piece and then another piece. And so for linear elastic fracture mechanics, we actually start from the point of observing that there is a crack in a component, and we go from there. There were observed to be kind of two, let's say, rates of failure with cracks. And so you can have cracks that are slow and stable. And when we say slow and stable, we mean something on the order of fractions of an inch per minute. Okay. So it is observable that the crack length is increasing, but the whole thing is not going to fail within minutes. And then there was also observed to be a faster rate, right, which is unstable. And these are the crack propagations that lead to catastrophic failure. And that can be hundreds of feet per second. All right. And so when we think about that sort of Comet aircraft, the fuselage broke apart very quickly. It like sort of exploded in the air. And so that was an example of cracks propagating at hundreds of feet per second, right? Sort of like too fast for humans to react and save and fix things. And so these were done in experiments of a notch in a tensile specimen. So I'll just kind of draw that here. All right, so if here's our tensile specimen, and we have a load that is manifested as just an axial stress going in this direction. If this was a tensile test and we were trying to measure modulus and yield strength and things like that, it would not have a notch, and we would assume that that stress is applied throughout the entire cross section. When there is a crack, the first thing that you can immediately see is that instead, if we look at a cross section right through where that initial crack is, now the area through which that force is goes through is much smaller, right, depending on how big the crack is. And so our nominal stress is higher now, right? So when we apply something like concentration factors for these kinds of problems, and we say something about like the nominal stress, right? That would be the contact area, or the cross-sectional area minus where that crack is. So it does not include that. So the nominal area is lower. So the first experiments that were done is creating notches of different sizes, Right, so I'll draw that on the x-axis here. And so I'm going to call that a critical crack length in inches. Usually that is shown by the little letter A. So that's how we're going to refer to it. And then so this plot I'm going to make goes up to about 12 inches here and starts at, let's call it like 1 inch. Okay. So let's say that this is like an aluminum plate with a crack, and this is the initial crack in the plate. Okay. It says here that the plate, just in the caption of this figure, is 24 inches wide and 0.1 inches thick. All right. So this is kind of a thin plate, right? So plane stress, and so it's got a notch. It's being pulled. And then we can plot on the y-axis here the gross failure stress. Okay, so what was the stress at which that crack just propagated all the way across quickly and the part failed? And so this is going to be in kpsi. And it's going to go up to about 60 here, and then down to 0. So I have like 20, 40, 60. And when I plot this, it's going to look a little bit like those SN curves, but put that sort of out of your mind because we're talking about something different now. But when you have a critical crack length that is very long, like 12 inches, which would be half the way across this plate, then the failure stress is at its lowest. So you would get a point kind of about here. And in this case, this is for a particular aluminum alloy. Okay, and then at the opposite end, if the critical crack length is 1 inch, then we have to pull with a lot higher stress to get that thing to break. And so we're up here, right, at like almost 60 kpsi. And then the data points will go sort of like this, right? And we don't really approach something asymptotically like we do with the SN curves, but we get this kind of inverse type relationship. And I'm going to draw the line as they've drawn it in the book, even though it doesn't fit through all the data points. Okay, and so I'm going to label a few more things on here. So up at the top of this plot would be the ultimate strength. So that's, in this case, like 69.5 kpsi. Okay? So we know that we're not at the ultimate strength. But when it's at the critical crack length of, I think it's about 1 inch or lower, like we're kind of at the yield point. So the yield point for this material is 58.8 kpsi. So when you get to crack lengths kind of an inch or two or smaller, then you really have to pull on it sort of up to above the yield point. But when you are below you can have a crack in there such that you pull on the whole specimen with a stress lower than the yield point. And so anything below, like anything above here is the yield point, but anything below here is below the yield point, right? And so this is not the way of thinking about the stress life method with number of cycles, but rather now we're thinking about the crack length. You could consider the crack to be a flaw in the material, right? So it's just something that does not hold any stress. And then this line that I've drawn on here, I'll sort of highlight it in a different color right here, can be represented by a constant that incorporates both the stress and the crack length. So when that happens, we're going to call this a critical, I don't know, we could call it the toughness, right? Fracture toughness. And it's going to have a constant value. And it's going to have weird units. So it's 110, and then it's KSI times the square root of inches, okay? So we'll see where that comes from in a few minutes. But that constant, that sort of fracture toughness, is a material property that you can look up for different materials. Okay? And that specifically refers to how concentrated the stress is at a crack tip in that material compared to the stress in the far field, the stress that you're applying. So that's kind of one way of interpreting that fracture toughness value. So if we go back and think about the problem or the setup here of this tensile test, and we think about a crack that's pre-notched in there, right? So we don't care about what the fracture face looks like so far. It's just pre-notched into there. And then we start to pull on this thing. I said that we were going to talk today about linear elastic fracture mechanics, right? But you can make an argument that at the crack tip right there, there's no possible way we could have elastic deformation, because we're literally taking the material and breaking a bunch of bonds and warping it, and so there must be some plastic deformation there. And so I want to say your intuition is not wrong, but in linear elastic fracture mechanics, what we do is we compare kind of the zone of that plastic deformation with the larger idea of the stress affecting that crack. Okay? So as long as this little plastic zone remains small compared to the length of the crack, A, then we can assume that most of this material, even near the failure area, is in a linear elastic regime. So that's why we call this linear elastic fracture mechanics. And it does provide pretty good engineering results, right? That's where this kind of plot came from, right? Which is assuming there's a factor we can multiply to compensate for that very small plastic zone in the middle of a larger elastic field. And we already understand a lot about elasticity and multi-axial stresses and those kinds of things. So we're going to leverage some of what we already know in linear elastic fracture mechanics. When we cover this, then we can go back to chapter 8 and talk a little bit about elastic plastic fracture mechanics. And that'll set us up for low cycle fatigue and things like that. Okay? So that's kind of just setting the stage for why we're covering this, and why I didn't cover it before, because I didn't want to cover like the introduction to linear elastic fracture mechanics, but then say we'll get back to that later. And so we're doing it now right before we use it in chapter 8. There are 3 modes of crack propagation that are dependent upon the ways that the stresses are applied to a surface or a sample. And so the first one is called mode 1. All right, I'm going to do my best to draw this. It's also in the textbook in a nice fashion. Let me just draw it like this. And we need the top on, and then we'll be mostly good. Okay, so pretend that this is a nice drawing. I'm going to fix one line. It's bugging me. Okay. Okay. So in this case, our initial crack is in this face here, and we are going to be pulling up at the front edge. Don't do that. The front edge, basically like this, just trying to straight up open that crack, right? So this is called mode 1. And if you need an intuitive model, I'm a visual thinker. I always need these intuitive models to think about how this crack is opening. This is like Pac-Man's mouth, right? It's opening and closing. And so when Pac-Man is opening his mouth, right, it's that old comic, or the old video game, it's a mode 1, right? You just pull on it in a tensile mode and it wants to open the crack. This is considered to be kind of the one that we're going to study in detail, like the quintessential crack opening, because it creates kind of the most intense situation at that crack tip, right? We're literally just trying to open the crack directly. Okay. There's another mode, which is mode 2. I'm going to see if I can draw it next to it. And mode 2 is basically where you are applying loads and you create like a stair step. All right, so let's draw it like this. And then your crack is actually forming like here, and it goes back just a little bit. And so you can imagine there's a load on the top plate pushing backward, and correspondingly on the bottom plate kind of pushing forward. And so my mental model for this is if you have a stack of playing cards and they're stacked up nicely, and then you shear the top, and if it's a nice set of playing cards, then they will all, fan out. And so you're creating stair steps. And so that's mode 2 crack opening. And you can see now that the stresses at the crack tip are going to be very different in this case. On mode 1, you have tensile stress at the crack tip trying to open that thing up. In mode 2, you're actually compressing one side of the crack and putting tension on the other side of the crack, and it's totally in a different axis, right? So that's mode 2. Mode 3 is kind of a twisting motion. So let me do my best on this one. Okay. Oops, I've left off an entire section here. All right, sorry, start over. There we go, just draw it how it is. Okay. All right, so the crack is in here, right, in that colored in area, and we're shearing it. So we're taking both sides above and below that crack and moving them side to side. So this is mode 3. And this reminds me of if you had a bunch of fins lined up and you were going to create a spiral staircase, and you started rotating the fins around to create that spiral staircase. That's kind of what this mental model is, kind of a twisted staircase. Okay. And so you can see now that the stresses are going to be yet different again in this mode. We're going to look mostly at mode 1 because I said it's kind of this quintessential, most severe crack opening. But you can think of situations where these other types of modes exist. The one that I think of most commonly that has mixed mode fracture is earthquakes. So when the tectonic plates move, right, there can be all kinds of different pressures and stresses that build up to cause them to slip, and then they slip against each other, and they can slip sideways. You can you don't really have a lot of mode 1. It's usually mode 2 and mode 3, but you can do the stair steps, or you can have twisting, and then the way that manifests at the Earth's surface can be different ways. You can have longitudinal waves, the up and down waves, right? And so earthquakes are kind of a mixed mode, but there's all kinds of examples of this, so it's kind of fun to think about that. And so there are people who studied these types of crack geometries in detail, and they've come up with sets of equations that describe the stress state at the crack tip, right? Because that's what we really care about. We want to, if we know sort of this, fracture toughness for a material, this K sub C, and we want to apply it to our loading conditions, right? We don't know what's happening at the crack tip, but we know what the loads are in the vicinity of that crack. Then we want to be able to compare with that and apply it. All right, so I'm going to write some equations on the following slides. So let's just first look at mode 1. Okay, and we are going to be looking at a little stress element that is inside of at the crack tip inside of a larger specimen. All right, so I'm just going to draw sort of a schematic over here. I'm just going to draw it once. Okay. So we will have sort of a crack here. I'm drawing these wavy sides because this is a cutout in a larger component. Okay. I'll have this here. I'll go back to like there. Okay. And yeah. So this is our crack that we have right here that I've drawn in bold. And we have like sort of a far away loading, right, in the far field that's causing this. And then we're going to look at a little stress element right here. Just draw it like this, right? And so we will have some things that we care about, like how far is that from the edge of the crack? We're going to call that little r, right? That's a radius. That's how far away it is. And then we'll also define an angle, which I drew the r right where the angle needs to be. Just a second here. So this will be r, and this will be some angle theta. And then we'll think about the stresses at that little element. And you will probably start to think, okay, if r goes to 0 and that element is on the crack tip, my stresses are going to go to infinity because it's kind of like a discontinuity in the material, right? It's no longer a continuum. All of our equations break down. So that's one thing that we'll come up with in these equations, is that if r goes to 0, stress goes to infinity. But we will have some other stress elements that we can define. So we can define sigma x, so that will be laterally across the page. Sigma y, up and down. And then sigma z will be coming out of the page. We're first going to assume that this is a thick plate. So unlike the thin notch specimen we had before, which was in plane stress, this is going to be in plane strain. And what that allows us to do is say that there's no stress in the z direction because it's a thick plate. Okay? And we're in mode 1 here. So we're just going to be able to say, based on those two reasons, that sigma z equals 0. So in mode 1, we'll have no stress along the crack at its tip through the thickness. Actually, hang on a second. Nope, I think I might have lied. We have a stress, but it's just based on the other stresses. Hang on. Got a little ahead of myself. Okay. We'll just leave that empty for now. Okay. All right, so we do have a sigma z. So let's write down expressions for sigma x and sigma y. So sigma x is going perpendicular to the loading direction. So this is mode 1, so we'll have k, big Roman numeral 1, divided by the square root of 2 pi r. And then we'll have some terms that have to do with the angle, right? And so it's just some longer terms. So we'll have cosine theta over 2 times 1 minus sine theta over 2, and then sine of 3 theta over 2, the product of those, plus some sigma x, if there is any in the far field, plus, come on, what I'm going to write as order, so this O in parentheses, of the r to the 1/2. So we can look at that equation and see how it aligns with our understanding, right? So we're in mode 1. So we have K1 at the beginning. So that's going to be our fracture toughness in mode 1. And then in the denominator, we have square root of 2 pi r, right? So if you've been in any other classes where you looked at how something at one point affects something at another point in a continuum, right? We always go with the sort of the square root of the distance we are away in polar coordinates. And that's where this 2 pi r comes in. And so you can see here now that when r goes to 0, this stress goes to infinity. So so when we're considering this, we don't actually have r go to 0, but we look at what those stresses are locally for non-zero values of r. And then we have a bunch of geometric terms. And then we're adding on this sigma x naught. Let me just underline that so you know what I'm talking about. And so this would be like if we had any stress in the far field that was affecting it. That would be superimposed onto the local stress that we have near the crack tip. And then we have another term here that is a weird notation, but it's the order of r to the 1/2. So that means like, is it, single microns? Is it tens? Is it hundreds? Is it whatever? So how far away are we? And r is usually quite small. So this term here is actually a higher order term that usually goes away. And most textbooks actually will just omit this. They don't even have it in there. And if we don't have anything in the far field, then it simplifies down to just that first term. Okay, so that would be in the x direction. So now let's look in the y direction. We'll have something similar. So we still have that k1 divided by square root 2 pi r, because we're in the same mode, we're the same location. And then some of these geometry, so the geometry terms are similar, but not exactly the same. So we still have a coefficient of cosine of theta over 2. And then instead of 1 minus sign, we have 1 plus sign in the middle here. We still have the same product, sine 3 theta divided by 2. Then we'll add on a higher order term of r to the 1/2. Okay. In this case, we have this stress field, and I'm trying to reconcile that addition that we had of theta x naught here in the first one as a far field term, but that's not included in the second term, even though sigma, the normal stress in the y direction is what we have in this coordinate system for mode 1 opening. So I'm wondering if that's an error in the book where it needs to go on x instead, or on y instead of x. I'll have to go back and look at that. Otherwise, the terms are very much the same. So these stresses are related. And then we also have, in this case, a tau xy. So that's going to be, if we have our cube here, tau xy will go across the top this way, and then up and down the sides like this. It'll be on the bottom, and then on this side as well. Just because of where the load is applied, and you can see that as we open that mode 1 crack, that we will have a little bit of an angular sort of opening, and so that's where that tau xy comes in. It's a combination of those effects. And so we also have a tau xy, same coefficient, and then we'll have a little bit of a difference on the geometries here. So sine theta over 2, cosine theta over 2, cosine 3 theta over 2, and then plus those higher order terms that we're just going to not think about. Okay. And so I said I'd come back to sigma z. So there is no applied stress in the z direction. All there is a combination of stresses in x and y. So we're just going to say that it's the Poisson's ratio. So we're going to go back to kind of Hooke's law here. So it's the Poisson ratio times sigma x plus sigma y. So that'll be our sigma z. The other shear stresses are 0, so tau xz, tau yz, those are 0. So this is our plane strain conditions, and then these stresses at that crack tip. The stresses for each of these components for modes 2 and 3 are also defined, but it doesn't make sense if we're not going to do like sort of an example problem and look at those magnitudes and talk about them in more detail. I'm not going to put all of those equations on these slides. So anticipate that you may have to go back and plug in some numbers and look at the magnitudes in like a problem set, but we're not going to do that in class today. I want to move on and just get to the definition of these stress intensity factors or fracture toughness. Okay? So I mentioned before that the capital K, these factors, fracture toughness, can be thought of, this K1, K2, K3, thought of as kind of concentration factors of how a far field stress is affecting the near field and how that's going to lead to crack propagation. And so we are going to define the K here. All right, K is equal to an equation that has the form of stress times the square root of the length of the crack, right? So I mentioned that the fracture toughness had these weird units of pressure times square root of length. And so it comes from the definition of this form here. So we have a stress, and then we have some geometric factor out front. We'll call it C, and if it's in mode 1, we'll call it like C1. So that's kind of a geometry factor, depending on whether the crack is in the middle of the plate, at the edge of the plate, and other things like that. So it's going to take on that form. And so if we then look at I'm just going to tell you what these things are. If we go back and look at elasticity theory and how that geometry affects that number, we find that this factor here is equal to square root of pi, right? And so then our new definition for this fracture toughness is stress times the square root of pi times the crack length, so pi a. And then we're going to say that for any K that's defined, we want to compare that with the material property, right? A critical fracture toughness. And so the way that we define that is a Kc, we'll call that like the fracture toughness for a critical crack in some particular mode, right? So I'm going to call it K1C. So if you look up that number for materials, that's what you're going to find, the K1C. And then what we're going to do is then compare that for, if this is a design situation, right? Compare that to the crack dimensions and the stress state and the geometry for a particular plate, right? So we're going to use it in the same exact way that we viewed something like a failure criterion and a yield stress. We're going to compare, instead of yield stress, we're going to compare a fracture toughness. The book gives some nice tables of some examples of these. So I'm just going to write down a few on the next slide just to give you an idea. So if we take like AISI 1045 steel, and this was measured in a plate form at room temperature, then it has a K1C of 46 KSI square root inches, which is equal to 50 megapascal square root meters. Okay. We've been using mostly English units in this class so far because a lot of these societies, at least in the United States and in the UK, who developed a lot of these standards, they all used English units, but we may have some problems as well in SI units. And for reference, the yield point of this same material is 39 KSI, and, which is equal to like 269 megapascals. Okay. And so generally the orders of these things follow each other, but you can't predict one from the other, right? Because the yield point is a sort of a continuum property that was determined from a tensile test. And the K1C is also a property, but it includes the flaw length in that. And so it's more complex than that. So you cannot just infer one from the other. There are some limits on when these equations apply. So if we are assuming these plane strain conditions, then we have to have a thick material. And so the book gives a nice rule of thumb here where they say the thickness, they call it capital B, has to be greater than or equal to 2.5 times the ratio of this K1C to the yield point to the second power. All right, so if we want to make sort of something with units of length, then we do pressure squared divided by itself and then square this square root, and we come out with a unit of length. Okay. And so this can be helpful if we know what our loading is and we know what the properties of the plate are, the material are. We can use this as sort of a design guideline and say, if I want to apply these plane strain conditions, how thick do I need to design this plate? Okay. So the next thing that we'll talk about is how to use this in design. And I think before I launch into that, I think we're going to stop there for today, and then we'll pick that up on Thursday, and I'll show you how to determine from geometry what these factors are and how to calculate the like kind of what values we're comparing to the K1C in a few design situations. And that will set us up nicely to then move on to not just a stress applied, but rather cyclic stresses applied when there is a crack present for some of that cascading safe design where even if you have a crack that initiates, how can you keep it in a slow growing stable regime so that it may be picked up in an inspection cycle before there's catastrophic failure. Okay? I believe the exams are due tonight. I've been trying to knock down every question that's come at me through email and through the discussion board. So if you have further questions, send them my way and I will try to answer them before the deadline tonight. All right, so thanks everybody. See you on Thursday.